Welcome to my video lecture series in Object-Oriented Programming. This is Professor Janice Raymond Tan from the College of Computing and Engineering.
For this video lecture, we will cover the topics about the class relationship, which is class aggregation. Throughout this video, we will discuss what is class aggregation, multiplicity, aggregation representation in UML class diagram, and how to translate class aggregation into code.
Objects sometimes need to have ownerships. Ownerships means that whenever an object is owned by another object, it will not be possible to assign the same object to another object. In OOP, we can achieve this type of class relationship using class aggregation, which is a special type of association. Throughout this video lecture, we will focus on whole part or part of relationship, which is the class aggregation. What is class aggregation? Aggregation is a specialized form of association where all objects have their own life cycle, but there is ownership. This represents a whole part or part of relationship. This is represented by a hollow diamond followed by a line. The hollow diamond should always be beside the class which is considered as the whole. Aggregation refers to the formation of a particular class as a result of one class being aggregated or built as a collection. For example, the class library is made up of one or more books among other materials. In aggregation, the contained classes are not strongly dependent on the life cycle of the container. In the same example, books will remain so even the library is dissolved. We call aggregation those relationships whose objects have an independent life cycle, but there is ownership, and child objects cannot belong to another parent object at the same time. Aggregation is usually unidirectional. Only the whole class is aware and not the other class, which means that what we need to do is to define only a class field of the another class inside the whole class. Factors to consider to identify as a class aggregation. We call aggregation those relationships whose objects have, number 1, an independent life cycle, meaning can live on its own even when deleted one of the two objects. Number 2, whole part relationship. An object is considered the whole and the other object is a part. Number 3, there is ownership, one class object and the other object. And number 4, child objects cannot belong to another parent object. Multiplicity. Multiplicity can be set for attributes, operations, and associations in a UML class diagram and for associations in a use case diagram. The multiplicity is an indication of how many objects may participate in the given relationship or allowable number of instances of the element. So just like in association in our previous lesson, multiplicity is also applicable in class aggregation. So same treatment will be used. Aggregation representation in UML class diagram. Aggregation is usually unidirectional. Only the whole class is aware and not the other class, which means that what we need to do is to define only a class field of the another class inside the whole class. In our case, let's take an example of a cell phone and a cell phone battery. A single battery can belong to a phone, but if the phone stops working and we delete its reference object, the phone battery will not be deleted because it may still be functional. So in aggregation, while there is ownership, objects have their own life cycle. The figure shows the relationship of a cell phone and a battery class. They both have independent life cycle wherein in the sample code translation later, you will observe that we will not instantiate a battery object inside the cell phone class because if we do so, once we delete the cell phone object, the battery which we instantiated inside the cell phone object will also be deleted, and that is not the idea of class aggregation. Since aggregation is considered unidirectional, only the cell phone class is aware between the two classes. As you notice in the figure, only the cell phone class has the reference to the battery object. The figure shows a whole-part relationship, cell phone being the whole and the battery as the part. To make our program efficient, we define ID class fields for both classes to provide identity for each object and help us control the aggregation process. Notice in the hollow diamond symbol beside the cell phone class, which makes it the owner of the battery class. Remember that in aggregation, there is a sense of ownership, which means in our example, once a battery is installed in a cell phone, the battery cannot be shared with other cell phones. Therefore, it is owned by that particular cell phone. At the same time, multiplicities such as 0 or 1 and 0 or 1 are used in this example. The relationship will be read as follows. So let us consider first from cell phone to battery perspective. Every cell phone may or may not have a battery, and that is the 0 or 1 from cell phone to battery as shown in the figure. In real world scenario, it is possible for a cell phone not to have its own battery. Again, that is the 0 in the 0 or 1 here, multiplicity, and additionally, a cell phone can only have one battery installed, and that is the 1 in the 0 or 1 multiplicity. So combining the two cases makes it a 0 or 1 relationship. And to achieve aggregation and to make every cell phone object aware of the details of its battery object, you need to define a battery object as a class field of the cell phone class. Making it null as a default value makes it possible to a cell phone or for us to have a cell phone object not having a battery at first. In the cell phone parameterized constructor, we only accept values for ID, brand, and model. We did not include the battery object as a parameter even though there is a battery class field defined in the cell phone class. The reason is because it is possible that one may or may not install a battery in a cell phone. A method named installBattery, which accepts a battery object as its parameter, will set the relationship between the two classes, wherein anytime we want to install a battery in a cell phone, we will call this method, passing a battery object as its parameter. This method also controls the multiplicity of having only one possible battery object to be installed in a single cell phone object. This method indicates the functionality of aggregation wherein we cannot connect an object to another object. Since the sample code translation later will be dealing with multiple battery objects, we will define a list batteries collection object in the main class to handle the storage of values for every battery object being created and will serve as our battery inventory. An uninstall battery method which accepts a list of batteries object collection as its parameter from the main class as our inventory of batteries as its parameter will help us to locate which among the battery objects is to be uninstalled in a given cell phone object. This method indicates the functionality of aggregation wherein we can disconnect an object from its previous related object. Now, from battery to cell phone class perspective, again, from battery to cell phone class perspective, you will consider this particular multiplicity. Every battery may or may not be installed in a cell phone. If it is to be installed in a cell phone object, it will not be available for others unless we uninstall it. In the real-world scenario, it is not possible that more than one cell phone object is using a single battery. The set installed, which accepts a Boolean value, setter method will be called whenever we will install, that is true, or uninstall, that is false, a battery object in a cell phone object. Notice that the default value of Boolean is installed class field is false inside the battery class. This is to simulate that a battery, unless installed on a cell phone, is by default considered to be not installed upon creation. In the battery parameterized constructor, we only accept values for ID and capacity as its parameters. Now, how to translate class aggregation into code? The key event code shows how to translate the cellphone class from the UML class diagram into its corresponding Java code considering its class fields, constructors, and methods. The red text indicates the functions of each block of code. First, we define the class fields for the cellphone class that will describe each cellphone object to be created. Namely, we have the ID of data type integer that will store a unique number to define its identity, the brand of data type string that will be used to store the manufacturer of the cellphone object, the model of data type string that will be used to store the model of a specific cellphone object. Example, if Apple is the brand, then the sample model is iPhone 12. Lastly, is a battery object that is default to be null, meaning every time we will make a cell phone object, we need to install a battery. Battery object as defined in the battery class will have its own set of class fields that will describe each battery object to be created. We defined a single parameterized constructor that will be used to assign the initial values for the class fields of a cell phone object such as ID, brand, and model. Notice that we did not include a battery object in the parameter. This is because, in accordance to our UML class diagram, a cell phone can have 0 or 1 battery. By not including the battery object as a parameter in the parameterized constructor of the cell phone class, we can achieve the 0 in the 0 or 1 multiplicity. But if in case you realize that the multiplicity from cell phone to battery is just 1, meaning it is required that a cell phone should always be created with a battery installed by default, you should modify the constructor by including the battery object as one of its parameter. This is just a simple scenario that your program code will always depend on how you analyze the problem based on your UML class diagram. Now, going back with the original UML class diagram and code, we defined an install battery method which accepts a battery object named battery as its name inside the cellphone class so that we can assign a battery object in a specific cellphone object which does not have one. Notice that inside the method body, we first check if the battery object has a class field of the cellphone class is still null. Remember that the initial value of the battery object class field is always null, meaning no content or no details yet, no battery is installed. Here, we use the this keyword to reference the battery class field and comparing it to null. Another condition is to check if the battery object as a parameter of the install battery method is not yet installed to any cellphone object. This is through calling the isInstalled getter method of the boolean isInstalled class field of a battery object, which is by default false and will change to true once already installed. If both conditions are true, then we can install the battery object as the value of the battery class field of the current cellphone object. Executing this .battery is equals to battery will help us assign the parameter object battery as the value of the cellphone object's class field named battery. By calling the isInstalled setter method of the isInstalled class field of the battery object and passing true as its parameter will now make the battery object installed. To achieve the idea of aggregation not having temporary ownership, we defined an uninstalled battery method which accepts a list collection object of batteries which serves as our battery inventory inside our main class. The idea is simple. We should first check if the cellphone object which will be uninstalled a battery should have a battery installed. because in reality, we can only uninstall a battery if and only if a cell phone already has its battery. After checking, we will loop through each battery objects inside the list collection object of batteries and will check for every iteration of the ID of the battery currently installed in the cell phone is equal to a specific battery from the list. We will check if the battery of the currently installed in a cell phone is equal to a specific battery from the list. This is how important the ID is so that we can have a way to track and check the specific battery object from the inventory. If the ID has a match, what we need to do is to simply set the isInstalled class field of the battery object from the list collection to false, followed by setting again the class field object battery of the cell phone to null. Lastly, we included a getCellPhoneDetails method and a getFullDetails method to print the full details of a cell phone object. Now, let us go with the battery class. The given code shows how to translate the battery class from the UML class diagram into its corresponding Java code considering its class fields, constructors, and methods. Again, the red text indicates the functions of each block of code. First, we define the class fields of the battery class that will describe each battery object to be created. Namely, we have the ID of data type integer that will store a unique number to define its identity, capacity of data type string that will be used to store the battery capacity of a battery object, and lastly, we have the isInstalled of data type boolean, which is by default false, meaning every time we will make a battery object, it is not yet installed to any cell phone object. We define a single parameterized constructor that will be used to assign the initial values for the class fields of a battery object such as ID and capacity. We performed encapsulation in the battery class by defining the class fields as private and defining getter methods for ID and isInstalled, and a single setter method named setIsInstalled to change its value. We did not define a setter method for the ID class field in this example because we will not allow modifying the value of the ID class field. Lastly, we included a getBatteryDetails method to print the full details of a battery object. Now in main.java, we first create a list batteries list collection object that will serve as the inventory of all possible batteries to be created in our program. In our case, we will store two battery objects as elements of the list collection. Notice that the list batteries object is defined as static and outside the main method, and the battery inventory method so that it will be accessible in all methods within the class. Inside the main method, we created two cell phone objects which will be assigned with a single battery each that will come from the list batteries object collection. We also created two battery objects and added them in the list batteries object collection for the inventory by using the add method of the list collection class. To perform aggregation or temporary ownership of batteries for each cell phone object, we invoke the install battery method that will be used to assign the battery for a given cell phone object. The battery of object from the list batteries at index 0 will be installed inside the cell phone object 1, and the battery object at index 1 will be installed inside the cell phone object 2. Then we will print the details of each cell phone object with the current setup using the getFullDetails method of each cell phone object. And this will be the output upon execution, showing the full details of each cell phone object, including the details of the batteries installed. Then we will print the details of each battery object by calling a battery inventory method of the main class, which iterates to every battery object stored inside the list batteries collection. And this will be the output upon execution, showing the contents of the list batteries object collection. Notice that both batteries are currently installed. Then we try to uninstall the battery from the first cell phone object, having the battery ID is equals to 1 by calling the uninstall battery method of the cell phone class. We printed again the details of each cell phone object with the new setup using the get full details method of each cell phone object. And this will be the output upon execution, showing the full details of each cell phone object. Notice that the cell phone object having ID is equals to 1 does not have the battery installed anymore since we uninstalled its battery. Lastly, we printed again the details of each battery object by calling a battery inventory method of the main class which iterates to each battery object stored inside the list batteries collection. And this will be the output upon execution showing the contents of the list batteries object collection. Notice that the first battery object is now available since the isInstalled class field is now false. Additionally, notice that only the specific battery previously assigned to the cell phone object ID with object with ID is equals to 1 is the one which is affected and will not change the isInstalled class field of the other batteries in the inventory. The example code of aggregation simply indicates a whole part or part of relationship between a cell phone and a battery object. In a real-world scenario, a battery is part of a cell phone. Keep in mind that the given example is not always a scenario. The code you will produce will always depend on how you analyze the class relationship using the UML class diagram, including its multiplicities. Try to think of some real-world scenario that will possibly make use of other multiplicities. In summary, we could say that objects sometimes need to have ownerships, and ownership means that whenever an object is owned by another object, it will not be possible to assign the same object to another object. Aggregation is a specialized form of association where all objects have their own life cycle, but there is ownership. This represents a whole part or part of relationship. Like association, aggregation relationship can be 0 or 1, 1, 0 or many, 1 or many, and many to many. That can be achieved by adding multiplicity adornments to the line denoting the aggregation. We can call aggregation those relationships whose objects have an independent life cycle, has whole part relationship, there is ownership, and child objects cannot belong to another parent object. Aggregation is usually unidirectional. Now for this lessons activity, create a program with the following requirements. So take a screenshot of the given slide to show for you to read the requirements. And these are your tasks. You need to post the link of the working program code using your account in codeba.io and the screenshot of the UML class diagram created using the Amblet application inside the post tab of week number 13 channel of our MS Teams. That's it for now. Thank you for watching and hope you enjoyed this video. For inquiries, feel free to post your questions in our group chat. In our next video, we will discuss all about class composition. Don't forget to visit the links in the references section for more information about this lesson. See you in the next video.